All right, so this is going to be part 3 of arc length problems with parametric equations. So we have our problem up on the board here. Find the arc length of x equals t sine t, y equals t cosine t from 0 to 1. And we have our arc length equation right up on the board here. Okay, so first things first, find dx dt, find dy dt. So dx dt, just a little bit of product rule here. We're going to get sine t plus t cosine t, and dy dt we will get, well, that's just going to be a cosine t minus t sine t. Alright, so now we have everything that we need to be able to plug in to this equation, because we also have our bounds, which is 0 to 1 right here. Great. So let's do that. We have that the arc length is now going to be equal to the integral from 0 to 1. The square root of this is now going to be sine of t plus t cosine t, quantity squared. And we have a plus cosine of t minus t sine t, quantity squared, and we have a dt. Alright, so now we just got to square these pieces right here. Okay, so of course do some foiling. Alright, and we'll get a long square root of things. Okay, if we square sine of t, we're going to get sine squared of t. We square t cosine of t, we're going to get t squared cosine squared t. And then if we do the middle terms, well, we're going to get a plus 2t cosine of t sine of t. Awesome. Now we need to do the second piece, and this is going to be exactly the same, except now, and this is kind of like the part 2 video, so this looks familiar, I guess. We have a minus 2t cosine t sine t. So we'll write, and of course our t's are going to be on a different variable this time, so it's going to be plus t squared sine squared t plus cosine squared t minus 2t cosine t sine t. And we have our dt at the end. Okay, so doing some simplification here. As in part 2, as in that video, if you haven't seen that, go check it out. These pieces are going to cancel out. And now we're left with something a little more complex, but not by too much. We get sine squared t plus cosine squared t plus t squared sine squared t plus t squared cosine squared t dt. Alright, this will simplify down to, and just this will be 1 and this will be a t squared. Okay, so this is the same thing as saying the integral from 0 to 1 of the square root of 1 plus t squared dt. Now, how do we solve an integral like this? Well, this is a inverse trig substitution. Okay, so now we got to do that. Great. So we're going to set t equal to tangent theta. Right, this is a tangent theta case. Okay, and we know that we're going to have a 1 in front of the tangent theta because there's a 1 here. Okay, now that means that dt is going to be equal to secant squared theta d theta. So where t is 0, theta is going to be 0, and where t is 1, because that's our other bound, theta will be pi over 4. Okay, so now we have our bounds, we have our substitutions. Let's go ahead and substitute. So we're going to get that the arc length equals the integral from 0 to pi over 4 of, this is now just going to be a square root of 1 plus tangent squared theta times the secant squared of theta d theta. What do we know about 1 plus tangent squared theta? Well, that's secant squared theta. We take the square root of that, that's going to be secant theta. and we're going to end up with the arc length equaling the integral from 0 to pi over 4 of secant cubed theta d theta. And this is a whole different beast in and of itself, so I'm going to have to erase here to make some room. Alright, so how do we integrate the integral from 0 to pi over 4 of secant cubed theta d theta? Well, this is an integration by parts problem, right? So you may have remembered integrating this before, but this is actually a pretty tough integral. Okay, we can do integration by parts here, so we'll set u equal to, that'll just be secant theta, and we'll have dv be what's left, which is secant squared theta d theta. So v is going to be just tangent theta, and du is going to be secant theta tangent theta d theta. Okay, so now we have all the pieces that we need to perform integration by parts. So let's go ahead and do that. We get that this is equal to secant theta tangent theta evaluated from 0 to pi over 4 minus the integral of v du. Okay, v du is tangent squared theta secant theta d theta. And of course that's the integral from 0 to pi over 4. Now, what good does this do us? I have no idea how to integrate something like this. Well, actually we can just use our identity here. So we can rewrite this as secant theta tangent theta evaluated from 0 to pi over 4 minus the integral from 0 to pi over 4 of secant squared of theta plus, that's actually going to be a minus, it's going to be secant squared theta minus 1 times secant theta d theta. Okay, so what good does this do us? We can distribute secant theta, okay, and instead of rewriting that, I'll just do that right here. We'll get a secant cubed theta minus secant theta. And now we end up with that same integral again. Well, that's not a bad thing, because we can just do this, right? We can split apart this integral and have it be secant tangent evaluated from 0 to pi over 4 minus, it's going to be minus the integral from 0 to pi over 4 of secant cubed theta d theta plus the integral from 0 to pi over 4 of secant theta d theta. Okay, so why did I do this? Well, we started out with the integral from 0 to pi over 4 of secant theta d theta. So if I just add this over to the other side, we get the integral from 0 to pi over 4 of secant cubed theta d theta equals secant theta tangent theta. And we can just integrate this piece right here, I guess. This will be plus the natural log of secant theta plus tangent theta. And this will all be evaluated from 0 to pi over 4. Alright, so all I did for this piece, like for the secant theta, I integrated it, and since this is also going to be evaluated from 0 to pi over 4, I just stuck the evaluation on the outside of everything. Okay, now the last thing that we need to do here is divide by 2 on each side so we can actually get the answer to the integral from 0 to pi over 4 of secant cubed d theta. Okay, and if we just divide by 2, we'll get something like this. Alright, so now we need to do our evaluation step. Alright, and when we plug in pi over 4, well, secant of pi over 4 is going to be rad 2 because it's 1 over cosine of pi over 4, which is 1 over rad 2 over 2, that being rad 2. So we're going to get rad 2 times, well, tangent of pi over 4 is just 1, plus the natural log of secant of theta, again, that's rad 2. And tangent of pi over 4, that's 1. Okay, that's all going to be over 2. And we're going to subtract, well, what are we going to subtract here? Tangent of 0 is just going to be 0, so this piece goes away. What about on the inside here? When we plug in 0, secant of 0 is 1, and tangent of 0 is 0. So we're going to get natural log of 1, which is 0. Okay, so we're actually just going to be subtracting nothing. So this will be our answer. Actually, I can get rid of this times 1. This will be our answer. All right, and that's really it. Okay, so very involved problem. This is probably the, probably the most involved problem you would get for an arc length problem. But yeah, I mean, so we started out with our equation, we plugged in for that, then we had to do a inverse trig substitution that led to a secant theta d theta integral where we had to do integration by parts. So ton of Calc 2 work here. But anyways, that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for parametric and polar, the explanation video for arc length with parametric equations, in the next video in the series. See you soon.